Welcome to this lecture. In this lecture, we will discuss the partial fraction method to find the nth derivative of given function. So let us start with this example. We can see here function f of x is a algebraic function. This is fraction. To convert this function into the standard form, we will use the partial fraction method. Now let us see. We will write f of x is equal to x upon x minus 1 into 2x plus 3, which is equal to a upon x minus 1 plus b upon 2x plus 3 is equal to a multiplied to 2x plus 3 plus b multiplied to x minus 1 upon x minus 1 into 2x plus 3. This would be equal to x into 2a plus b plus 3a minus b upon x minus 1 into 2x plus 3. You can see now this both are equal. Here the multiplier of x is 1, so we can say 2a plus b is equal to 1. In addition, 3a minus b must be equal to 0 because there is no addition here. And 3a minus b equal to 0. Now we can solve these two functions and we would get a is equal to 1 upon 5 and b is equal to 3 upon 5. Let us put these both values in this and we got the partial fractions. We would now get f of x is equal to 1/5 multiplied to 1 upon x minus 1 plus 3/5 multiplied to 1 upon 2x plus 3. So now we got the standard forms. For these both functions, we would use this formula. For x minus 1, the value of a is 1, b is minus 1. And for this function, the value of a is 2 and b is 3. We can write differentiating f of x n times. We will get the nth derivative of x would be equal to 1/5 multiplied to minus 1 raised to n into n factorial into the value of a is 1, so we don't have to write anything, upon x minus 1 raised to n minus 1 plus 3 upon 5 into minus 1 raised to n into n factorial into value of a is 2 here, so we will write 2 raised to n upon 2x plus 3 raised to n plus. This is the answer. Here function f of x is given and we have to find the nth derivative. You can see we are supposed to use the partial fraction method, but there is no way in R we can convert this into partial fraction. So we will have to use complex function here to convert this function into partial fraction form. So for that we will write f of x is equal to 1 upon x minus ia x plus ia. This would become nothing but x square plus a square. And this is a complex function. And now we can write this as a partial fraction function. Here ia is constant. And to write them as partial fractions, we can easily write it as 1 upon 2ia into the bracket 1 upon x minus ia minus 1 upon x plus ia. We would get 2ia extra in the numerator, so we have divided it with 2ia. We can see now both of these functions are in standard form, and we can use the formula here. We can use this formula. Here the value of a is 1 for both of the functions, and the value of b is positive and negative ia for both functions. Now we can write differentiating f of x n times, we will get the nth derivative would be as 1 upon 2 ia is constant. We will write it as it is. For the functions, we would write it one by one. For the first part, we would write minus 1 raised to n into n factorial into, here the value of a is 1, so into 1 we don't have to write it, upon ax plus b raised to n plus 1. Here ax plus b is x minus ia raised to n plus 1. The same way, nth derivative of next function would be minus 1 raised to n into n factorial upon x plus ia raised to n plus 1. You can see this answer is correct, but this answer is in complex form. The question is not in complex form. So if possible, we are supposed to give the answer the same way as the question. So next, to convert it, we will write x is equal to r cos theta, a is equal to r sin theta, so that r square is equal to a square plus x square, and tan theta would be equal to a by x. Let us put those values. We can see the numerators are same, so we can take them common. So the nth derivative we can write, the nth derivative of f of x is equal to minus 1 raised to n into n factorial upon 2ia. Into the bracket, we would get r cos theta minus I r sin theta raised to minus of n plus 1 minus r cos theta plus I r sin theta raised to minus of n plus 1. We can take r common from both the terms and take it outside. We can write it in the denominator. We would get minus 1 raised to n into n factorial upon 2ia into r raised to n plus 1 into the bracket cos n plus 1 theta plus I sin n plus 1 theta minus cos n plus 1 theta minus I sin n plus 1 theta. So this step is nothing but DeMoiver's theorem. This is the formula. In this theorem, we are just supposed to multiply the power to the angles of cos and sin. It is the simple theorem. We have used that DeMoiver's theorem. So the next step would be f raised to n x is equal to minus 1 raised to n into n factorial upon 2ia into r raised to n plus 1. You can see here these two terms will get 0 out, and the remaining terms would be this and this. It would be 2i into sin n plus 1 theta. You can cancel out this 2i, so it would be equal to minus 1 raised to n into n factorial into sin n plus 1 theta upon a into r raised to n plus 1. Now let's multiply it and divide this with a raised to n plus 1. So we would get minus 1 raised to n into n factorial into sin n plus 1 theta. upon a raised to n plus 2 into a raised to n plus 1 upon r raised to n plus 1. As in the starting, we have assumed a is equal to r sine theta. So for this a raised to n plus 1 upon r raised to n plus 1, we will get sine raised to n plus 1 theta. So in the next step, the final answer would be the nth derivative of f of x is equal to minus 1 raised to n into n factorial into sine n plus 1 theta into sine raised to n plus 1 theta, and the whole term would be divided by a raised to n plus 2. This would be the answer.